Good day, everyone. I trust that you're all doing great. So, today we'll be discussing about one of the methods of solving differential equations iteratively. We're going to be talking about Picard's iterative method. But before we go on to talk about what Picard iterative method is all about, I would like to run you briefly on what a differential equation is and the various forms it could be in. So, a differential equation is an equation which involves a differential coefficient. Just like our regular equations, we have y is equal to 3x plus 4, for example. This is the standard form that we have. This is a linear equation, like we all know. An equation relating y to x. It's trying to tell us that y is related to x by the relation y is equal to 3x plus 4. But what if we have an equation of this form? dy dx is equal to 1 plus x squared divided by 1 minus y squared. Now, if you check the first equation I gave you, there was nothing like a differential coefficient there. But in the second equation that we have here, we have a differential coefficient, which is dy dx. Let's take another form of a differential equation. X partial derivative of u with respect to x plus y partial derivative of u, y partial derivative of u with respect to y is equal to mu. Now, this also has a differential coefficient, even though it's a partial derivative. And we are going to be talking about what differentiates a partial derivative and the ordinary derivative next. So, differential equations are divided into two. It could be ordinary differential equations or partial differential equations. So, if you have differential equations, it could be ordinary differential equations, ODE, or partial differential equations. Now, what is an ordinary differential equation? An ordinary differential equation is an equation which involves derivatives with respect to a single independent variable. So, if you check out the second of the equations I gave you initially, this equation we have here, you see that dy dx that we have here, we are trying to find the derivative of y with respect to x, which is just a single independent variable. But meanwhile, in partial differential equations is basically a differential equation that involves partial derivatives with respect to more than one independent variable. So that's what we call a partial differential equation. If we check out the second example that I've given to you here, we can see that we are taking the derivative of u, the partial derivative of u with respect to x in this first term, and we are taking the partial derivative of u with respect to y in this second term. So our two independent variables are what? X and y in this case. Meanwhile, our dependent variable is u. So that's what a partial derivative is. In summary, an ordinary differential equation involves taking derivatives with respect to a single independent variable, just like we have here. Meanwhile, a partial derivative or partial differential equation, involves taking partial derivative with respect to more than one independent variable, just as I've shown you here, dx and dy. So, next thing we are going to be talking about is the order and degree of a differential equation. So, the order of a differential equation is the order of the highest differential coefficient that is present in the equation. So the order of differential equation is basically trying to tell us the order of the highest differential coefficients present in a differential equation. So let's take about two examples of a differential equation. So we have L d squared q dt squared plus r d q dt plus q over c is equal to e sine omega t. So let's take a second one. 1 plus dy dx all squared raised to power 3 is equal to d squared y dx squared all squared. So remember that we said the order of a differential equation is the order of the highest differential coefficients that we have there in the differential equation. So if you look at this first example, we have two differentials. We have d squared q dt squared, which is the second derivative of q with respect to t, and we have the q dt, which is the first derivative of q with respect to t. Between the two differentials, the highest differential coefficient is the d squared q dt squared. So we say this differential equation is of the second order. Likewise, the same thing happens for the second example I'm giving you. Here we say dy dx all squared, 1 plus dy dx all squared all raised to power 3 is equal to d squared y dx squared, everything all squared. So in this case, we have two differential coefficients, dy dx, and we have d squared y dx squared. Note that in this case, we have dy dx raised to the power of 2, and we have the second one, d squared y dx squared. Regardless of whatever power that has been raised to, the differential coefficient has been raised to, d squared y dx squared remains the highest differential coefficient that we have there. And as such, this equation is also of the second order. So what is the degree of a differential equation? The degree of a differential equation is the degree of the highest derivative after removing the radical sign and fraction. I'll come again. The degree of a differential equation, so the degree of the differential equation is the degree of the So the degree of a differential equation is the degree of the highest derivative after removing the radical sign and fraction. So let's take a look at the first example. We already established that that's an example of a second order differential equation, that is a differential equation of order 2. Now, what is the degree of this differential equation? The first thing we need to do is we have to locate the highest derivative in the equation. So for the first example, the highest derivative is d squared q dt squared. Now you can see that for the first equation we have there is no radical sign, there is no fraction, so that has been taken care of. So in this case, the degree of this differential equation is going to be 1, because the power to which d squared q dt squared is raised after removing the radical sign and the fraction is also what? 1. So the degree of the differential equation is going to give us 1. Now to the second example, we have d squared y dx squared all squared on the right hand side, and we have dy dx all squared on the left hand side. Like we said already, the order of this differential equation is 2. It is a second order differential equation. So the highest derivative here is d squared y dx squared, and as such, we have no radical sign, we have no fraction, so we can easily see that the power to which the highest derivative, which is d squared y dx squared, is raised is 2. So the degree of this differential equation is going to be 2. So it is a differential equation of the second order and the second degree, for example 2. Meanwhile, for example 1, it is a differential equation of the second order and the first degree. I hope you all understand that. So moving on, we are going to be going into Picard's iteration. So moving on to Picard's iteration. So before we go into questions at all, I would like to show you how exactly we apply Picard's iterative method and in what situations do they apply. So Picard's iterative method is one of the numerical solutions or numerical methods for finding the solutions of differential equations, especially those whose solutions cannot be found analytically. So we have various numerical methods for finding the solutions of ordinary differential equations, and some of them include the Taylor series method, we have the Runge-Kutta method, and Picard's iterative method is also one of them. So in this video, that's what we will be focusing on. So what exactly is the Picard's iterative method and how does it work? So the Picard iterative method is used to solve ordinary differential equations of the form dy dx is equal to fx comma y, and we are going to be given conditions, the initial conditions. Y is equal to y naught for x is equal to x naught. So if you consider this differential equation, remember from what we said, this is a first order differential equation because the highest derivative that we have there is the first derivative. So that's where the order is coming from. I hope you haven't forgotten it. So the method for solving the Picard's iterative method goes thus. So if we take the integral of both sides, we write the equation first by writing dy is equal to fx comma y dx. So if we take the integral of both sides within the stated limits, we have integral of dy between y naught, which is the initial value of y, and y, is equal to the integral of f as a function of x and y with respect to x from x naught to x. So in integrating this, we have, sorry, I have to cut the screen. So we have y within the limits y naught and y to be equal to the integral of the function f with respect to x within the limits x naught and x. Sorry. So let me write that. Integral x naught and x. Good. So by plugging in the limits for the y, we have y minus y naught will be equal to the integral of the function fx comma y with respect to x and within the boundaries x naught and x. So moving on, we have y minus y naught is equal to the integral of fx comma y dx from x naught to x. Now by adding y naught to both sides, we have y will be equal to y naught plus the integral from x naught to x of the function fx comma y dx. So this, let's call this equation asterisk. So equation asterisk is the solution of the differential equation dy dx is equal to fx comma y subject to the conditions y is equal to y naught at x is equal to x naught. Now if you examine equation asterisk, because we said this is an iterative method, if we plug in y naught for y on the right hand side of the right side where the integral is, that integral of between x and x naught and x for the function fxy, if we plug in y naught, we have the right hand side to be y naught plus the integral of x naught to x fx comma y naught dx. So this is going to give us our first approximation y1. So using similar methods, we'll get our other approximation. So our second approximation y2 now becomes our second approximation y2, like I've said, is going to be y naught plus integral between x and x naught of f. Now instead of y naught here, it will now be y1 dx. So this is going to give us our second approximation of the solution. This is going to give us our second approximation. So similarly, our third approximation is going to be y naught plus the integral between x naught and x of f x comma y2 dx. So this is going to be our third approximation. So in general, we can keep going on and on depending on what the question asks of us. We might be asked to find 3 approximations using the Picard's iterative method. It could be 4 approximations, it could be 1 approximation only. But depending on what the question wants, this is how we'll go about it. So in general, we'll say yn is equal to y naught plus the integral between x naught and x, which is the limits that they give us. X naught is the initial value of x and y naught is the initial value of y, of f x comma y n minus 1 dx. So this is the general form to getting our nth approximation. So moving forward, there are key things we need to know. You know that for each approximation we get, the more approximations we get, the closer we get to our answer. So y2 is more accurate than y1, likewise y3 is more accurate than y2, and it goes on and on like that. So, and one more thing we need to note is this, that this differential equation, this method, this Picard's iterative method, is used to solve differential equations if the succession integration can be performed easily. So now let's take some examples to illustrate this method. So the first example we are going to be looking at, example 1. Using Picard's method, find y for x is equal to 0.1, given that dy dx is equal to y minus x divided by y plus x, and y at x is equal to 0 is equal to 1. So this looks like what we've talked about already. We have been given the differential equation of the form dy dx is equal to fx comma y. So in this situation, our dy dx, let's take a look at the solution. Our dy dx is equal to y minus x divided by y plus x, and y at x is equal to 0 is equal to 1. So this represents our function in x and y. We have our derivative already, and we also have our conditions, our initial condition. So we have everything set for us to solve this question. So the first thing we have to do is we'll express it in terms of our general method. So I want this to serve as a form of revision on the proof we just did. So let's do it step by step. So dy will be equal to y minus x divided by y plus x dx. So I'm taking the integral of both sides. We now have integral of dy from y naught, which is 1, to y will be equal to or let's call it y naught, will be equal to the integral of y minus x divided by y plus x dx, x naught and x. So writing it in general form, we have our y will be equal to y naught plus the integral between x naught and x of y minus x divided by y plus x dx. So let's substitute our values now. We know that y naught is equal to y0 and is equal to 1. And also x naught will be equal to 0. So on substituting that, we have our y to be equal to 1 plus the integral between 0 and x of the function y minus x divided by y plus x dx. Now remember that we said instead of having y on the right hand side, we have to input the initial value. For instance, we want to find y1. We have to input y0. General formula is, so the general formula is yn is equal to y0 plus the integral between x0 and x of fx comma yn minus 1 dx. Now in this question, we were asked to find the value of y for x is equal to 0.1. So in this case, to find y at x is equal to 0.1, we have to rewrite our equation as 1 plus integral from 0 to 0.1, which is our x that we need. Then y naught in this case is going to be y at 0. So let's write it as that. So instead of y naught, because we want the value preceding x is equal to 0.1, and the only value we have there is when x is equal to 0. So y at x is equal to 0 minus x divided by y at x is equal to 0 minus x. So we have this as 1 plus the integral from 0 to 0.1 of the function y at 0 is equal to 1. So we have 1 minus x divided by 1 plus x with respect to x. Sorry, I missed out the differential here. So we have y at 0.1 is equal to 1 plus the integral of 0 to 0.1 of the function 1 minus x divided by 1 plus x with respect to x. So on solving it using our calculator or any other software you have, we could solve it manually too, but that's not the point of this video. Y at 0.1 will now be equal to 1 plus 0.09062, and that gives 1.09062. So that's the value of y when x is equal to 0.1. Now let's take a second example. As you can see, we are asked to use Picard's method to solve the differential equation dy dx is equal to y plus e raised to power x at x is equal to 1. Correct to two significant figures, given that y is equal to 0 when x is equal to 0. So to solve this, we have dy dx is equal to y plus e raised to power x at y is equal to 0 when x is equal to 0. So we know our function in x and y as this. So we can write our Picard's formula. Our y at x is equal to 1 will be equal to y at x is equal to 0 plus the integral of y at x equal to 0 plus e raised to power x between the ranges x is equal to 0 and x is equal to 1. So it's going to be equal to the y at x equal to 0, which is the initial value, and the integral between x equal to 0 and x equal to 1 of y naught plus e raised to power x with respect to x. So let's substitute our values. So we have, on writing it, we have our y1 will be equal to 0 plus the integral of between 0 and 1 of 0 plus e raised to power x with respect to x. So our y1 now becomes the integral of between 0 and 1 of e raised to power x with respect to x. And this is giving us e raised to power x between the limit 0 and 1. So our y1 now becomes e raised to power 1 minus e raised to power 0, and that's e raised to power 1 minus 1. On punching this into our calculator, we have our y1 to be equal to 1.7183. So to correct to two significant figures, our y1 is going to be 1.7 to two significant figures. So with this, we've come to the end of the current video. We will still take more examples in the next video on Picard's iteration. Then we'll move on to something different as regards differential equations.